All right, well, I think we'll just get started here. So I've been meaning to do this talk for quite a while now. Back when we were still in 706, I did a very different talk on the operating system development community in general. Most of the feedback I got from that talk was that it wasn't technical enough and that people wanted to specifically hear about my operating system. So today we're going to talk about my operating system. Now, unfortunately, I've neglected to actually bring my slides. So our first step is to go get them from my website. So if you'll give me just a minute to make sure that these download. All right, that was really fast. I'm really happy with that. Let's get started. Make sure I can do that. Cool, all right. So the title of the talk is ToaruOS at 5 years. Originally, when I was making these slides, it was ToaruOS at 4 years, and it took me so long to get this talk scheduled and make the slides that it's now 5 years. We had a few delays. So most of the content in this talk is based on a survey that I gave out to several people over the past year of what they really wanted to hear the most about. So what we're going to talk about is some of the background of the project, what my original design goals were, and how the project has changed in its 5-year lifespan thus far. Then we're going to do a really, really technical deep dive answering what's actually a very common interview question, looking line by line through actual code of the operating system so you can see how it does stuff, and we'll talk a bit about some of the overall design while we're doing that. And I've got a bunch of demos I want to give, and then we'll talk a little bit about the future of the project and hopefully have time at the end for questions. So the first question I always get when I'm talking about my operating system online, when I'm not actually audibly talking about it, is, how the heck do you pronounce that? And the answer is it's ToaruOS. It's Japanese. It means something along the lines of a specific or a certain operating system, some such OS. And it's supposed to be a parody sort of there's this phenomenon in the OS dev community where you give your projects really, really generic names. There are actually several different operating systems called MyOS. So I wanted to do something that was along the same veins, but still sufficiently unique. So I was a really big fan of an anime series called Toaru Kagaku no Railgun, a certain scientific railgun at the time. So I used that in the name of MyOS, as well as in the design of the logo. So back when the project started in December of 2010, which is why we're approaching our 5th-year anniversary now, we did our first code commits in January 15th of the following year. It was a winter break when I was in college and wanted a project that would last me a while and get me into a lot of very interesting topics. And the first screenshot I have of the OS, which is right here, is from January 20th. It's not really doing all that much that's useful. Now I'm presenting on it. So the original goals of the project were that I wanted to learn POSIX. POSIX is a standard for operating systems. It's based on the original Unix. It's evolved a lot. OS X is a POSIX-compliant operating system. Linux actually isn't, which is a really complicated story. I wanted to learn a lot of x86 internals, systems-level things, brush up on my assembly a bit. And I also wanted to brush up on my C. C was a language I'd used before at the time, but it wasn't something I was really comfortable in. And now I can tell you I am really, really comfortable in C for building this. So I think I've definitely managed to meet that goal. The overall design of the operating system is it's monolithic and modular, very similar to Linux. There's sort of two camps in the operating system development world. There's people who build monolithic kernels because they're relatively easy and fast, and you can get things done very quickly in them. And then there are the die-hard research academic people who build microkernels and exokernels. Sorry about that. I'm a little nervous when I do public speaking, I'm sorry. Microkernels and exokernels and things like that, where you have to make a lot of trade-offs in terms of speed in order to provide usually more security, more safety, more reliability. The trouble is there's never actually been a microkernel project that's gone all that far. A very popular one that people like to talk about, and its ridiculously long development lifespan right now, is GNU Hurd, which has been in development for a very, very, very long time. So most operating systems that you use on a regular basis are going to be monolithic modular kernels. So ToaruOS is a 32-bit x86 operating system. I was working on a little Atom netbook 5 years ago, and it only supported 32-bit. So yeah, use what you got. It's Unix-like, but these days we don't quite go for as much POSIX compliance as we did in the beginning. And the most important feature of ToaruOS is it has what's called a compositing window manager, and we'll talk about what that is a little bit later on. Over the years, we've got a good bit of publicity. We showed up in a GitHub showcase on open source operating systems. That was a lot of fun. We got a lot of traffic from that. If you know what Phoronix is, there's a guy named Laravel who writes all the articles for it. It's a big Linux and open source news site. He wrote an article on the OS, and there's a website called OS News that also had an article on us. The biggest piece of publicity we ever got was that back in April of 2012, we released a joke distribution of the operating system called PonyOS. It was all My Little Pony themed. And more people know PonyOS than they do the actual ToaruOS. So it was a success in a way, but I don't like to associate myself with it too much. So as I said, the bulk of this presentation is going to be answering an interview question, actually. This is a very common one. You may have heard it before in an interview. Maybe you've given it in an interview. Our recruiting department doesn't like us to ask this one for various different reasons. And that question is normally phrased as what happens when you type google.com into your web browser and hit enter. We like to phrase it as what happens when you type yelp.com into a web browser and hit enter. But unfortunately, I can't actually answer that question because we don't have a web browser. So we're going to answer something a little bit different, which is similar to what we did when I went and grabbed these slides. We're going to answer what happens when we type fetch http://toaruos.org/talk/talk.pdf into a shell and hit enter. Slightly different question, but we'll hit most of the same key points. Before we begin, we need to talk a little bit about what the current state of the system is. What are we doing? We're going to assume that we're sitting at a terminal. We have our shell running. It's waiting for input. So what does that look like in code? So this is some source code from our shell. It's actually an advanced line editor. Supports complex line editing, like moving a cursor around, inserting text, stuff like that. And we're actually waiting for input over here on line 48 in this call to fgetc. So we'll skip over a lot of the details of how fgetc itself is implemented because it's not code that I wrote because it's part of the C library. And we'll skip down into the actual system call for read. So when we load a read from a terminal, we use the system call read. And it takes 3 arguments, a file descriptor number, a pointer to a buffer, and a length of data to be read. It needs to figure out what actual function it's going to call within the kernel to perform that read operation based on the file descriptor number that we gave it. For a read from our terminal, we're going to send it file descriptor 0, which is standard input. And that's going to point in the kernel to a pseudo terminal device, or a TTY, which means that eventually our read system call is going to call this function read PTY slave. And what read PTY slave does is it goes and looks in a ring buffer of data that's on this TTY that it hasn't read yet. And it says, I would like to read some bytes from this. And we actually asked for 1 byte because of how fgetc works. So what's our ring buffer doing? Well, it looks at the data it has available. It says, I don't have any data available. There's nothing for me to give you back. So it then sleeps, which we see it doing over here on line 63. And it's going to sleep until the other end of the TTY opens it up, or wakes it up. So our next stop on this journey is going to be what's going to wake up the shell, and that's our terminal emulator. So terminal emulator is the graphical application you see where your terminal shows up, and you see your shell, and you type your things in, and yada, yada, yada. So our terminal is doing a lot of things right now, but the most important thing that it's doing at the moment is it's waiting for an event to come in from the window compositor. which it's doing up here on line 1123 in this call to Yutani pull. It's also going to receive some other events while it's doing that. Maybe you move the mouse, it'll receive an event for that. Maybe it changed focus. Maybe you tried to resize the terminal, something like that. But the most important thing that we're waiting for is actually one of these things called a key event, which happens to be the first thing in our little switch statement here, so that's nice. Makes it very easy to find. So what else is happening while we're waiting here? Our compositor is sitting here, and it wants to get keyboard events from the actual keyboard, because that's where all of our events in the graphical front end originate, is from our compositor, and they need to come from actual devices. So our compositor does something really simple. It sits here, and it reads from a keyboard device file. And reading from a keyboard device file looks a lot like how the shell was reading from the T2Y. So we're going to skip a lot of the details of that and just say that, holy shit, everything is sitting here waiting. There's a lot of waiting in a modern operating system. You spend very little time actually doing anything until you start running CPU-intensive applications. This is really important for power saving, because if your CPU was chugging along and doing stuff all the time, your battery would die very quickly. So what's going to happen when we actually press the F key as part of this fetch command that we type? The first thing that's going to happen is we're going to get a hardware interrupt. And that hardware interrupt is going to cause the CPU to jump to a particular location that we've specified earlier in our keyboard driver that's going to run this function. Ooh, I have a laser. This function, which is going to then run some things where it talks to the CPU to actually get data from the keyboard controller, which is a piece of hardware that you actually hook your keyboard into. And it's going to give it back a scan code. And a scan code is not quite as useful as a letter. It's a little more complicated than that, because the scan code essentially just tells us what key on the keyboard was hit, but not what that key is. We'll have to do something with it later to figure out what that key was. But our keyboard driver is pretty simple. It just takes all of the scan codes it gets in and shoves them into this buffer that the client, in this case the compositor, can read. So we'll jump back into our compositor. It now has a key to read, and it's the scan code for the key F. So it returns from its read call here. And then it sticks that scan code into this big state machine that's going to turn it into the key F. Because we don't know what that is going into this. We just know it's a scan code with some random number. And the state machine has a big table of what those scan codes should end up translating into. But scan codes for keyboards are kind of complex. And some keys, when you press them, you actually get like 5 scan codes. So you have to run them all through a state machine before you can get a single key out of them. And then our compositor is going to take that, turn it into this key event that it uses internally, and send it off to another part of the compositor that's going to read it. That other part of the compositor is the compositor's main event loop, which is going to be doing a lot of things. It's going to be receiving input, or receiving various different events from all of the applications that are communicating with it. But it also receives messages from the keyboard driver that we just sent it. And what's going to happen is it's going to get this message key event that we sent it. It's going to see that it's a message key event, and it's going to call handle key event, fairly appropriately named, right? And handle key event's going to look at it and see if it's one of these weird key bindings we use in the window manager, because we can do really cool things like we can tile windows left and right, we can full screen them. And it needs to see if it's one of those first before it does anything else. But eventually, it's finding that all we did was hit the F key. So it's going to take that F key and it's going to pass it on to the client application that is currently the focused window. That's the terminal. So now we can go back to the terminal, and we can see that we've returned from this call to Yutani pull. We have a message key event. So now we're going to run this also appropriately named function key event. I'm not very original when I name my functions, aren't I? And what key event's going to do is something actually relatively similar to what the compositor did, in that it needs to figure out if it needs to do anything special with a key. So if you've ever been on a terminal and you hit like the arrow keys or function keys, page up, page down, there isn't a single character that your terminal can send to the application to represent that key. We instead use these things called escape sequences. So the escape sequence for F1 is this character octal 33 OP. They're really random. You got to look up tables for them if you want to be compliant with existing implementations. But all we sent was the letter F, so we're just going to jump through this and run handle input F, which is going to write the F to our TTY device, which means now we can go back to our shell, which is finally woken up from this call to fgetC. It has its own state machine to convert the escape sequences that the terminal can send it into key events again. It doesn't need to do any of that because luckily we're just an F. We don't need any special processing. But something we neglected to mention earlier is that our TTY is in a mode that has it not echo characters as you type them, which means the shell has to do that. So now the shell has to print the letter F, and then it has to add the letter F to this internal buffer that it uses so that when it returns from this call, it can actually read the full thing that we typed. Which brings us to, we printed the letter F, so now we have to go back to the terminal because now we need to actually print the letter F. So our terminal has a thread that's sitting around here trying to read stuff out of the TTY. This is all of standard output, standard error from the shell and whatever else is running in the terminal. And it takes that data and it sticks it into this other big state machine. And at this point, I have to say that terminals are really complicated. So back in the day, you had a black and white character cell display. It had maybe like 40 columns. It only supported a handful of characters. These days, terminals support all sorts of crazy things like Unicode text and full color foregrounds and backgrounds and really complicated cursor movements. And ToaruOS is no exception to this. My terminal supports all sorts of fun things and does it with this gigantic state machine. And we're going to skip over all of that because it's not really relevant because all we did was print the letter F. So at the end of the day, this big state machine calls two functions, cellSet and cellRedraw. CellSet just, it keeps an internal representation of what the terminal looks like, because sometimes we want to redraw characters, maybe we want to do scrolling, and you want to do scrolling correctly. You can't just like physically scroll the display. You have to redraw it with all your internal characters and all that fun stuff. And then cellRedraw is going to actually draw the glyph for the letter F into the window for the terminal. And at this point, we need to take a little bit of a break from looking at code. And we need to talk about how ToaruOS actually displays window contents to the screen. So as I mentioned earlier, ToaruOS is what's called a window compositor. A window compositor is an application that essentially controls the screen and does all of the drawing to the actual video device. And what it does is it does this through something that's called compositing, hence why it's called a compositor. And compositing comes from the early days of film and media, where you would take things and you would just stick them on top of each other to produce a final image. And that's exactly what our compositor is doing. It uses what are called canvases, which are essentially just really big buffers of 32-bit RGBA pixels that it stores in shared memory. So the compositor sees these, and the client application that owns the window will see them. And when a client application wants to draw into its window, all it does is set pixel values in this piece of memory. And then it has to tell the compositor, I've changed something, you should go redraw. So once we've received a bunch of redraw events, we take them all together and we redraw whatever things were edited and copy the result into video memory, and voila, we get a composited display with some nice pretty windows. So to actually draw text in our terminal, we're using a library called FreeType. Lots of people use FreeType. Apple uses FreeType in OS 10 and iOS. Every Linux distro uses FreeType. And it's going to actually draw the glyph into our canvas. And then we're going to tell the compositor that we've made some changes to the display and it should redraw them. So now we go back to the compositor and it receives a message saying that it should flip part of the display. It collects all of the different parts of the display that it needs to update. And then it's going to essentially run through all of the windows that it has to render, and it's going to bullet them, which means we're going to use a library called Cairo to do our actual pixel pushing. We support all sorts of interesting things like rotated windows and transparent windows and animations. And we draw all these windows, and then we copy them to the actual video memory. And now finally, after all of that, we have accomplished something. We've typed the letter F. So we repeat this process for all the other characters that we type, and then we hit enter. And now we get to go into our shell. So our shell is finally returned from this function call that it made to read a line of input. And it does some processing on the buffer that we gave it, because it needs to do things like splitting on spaces, handling quotations, expanding variables. And when it's done with all of that and figures out what it actually wants to run, it's going to fork. So forking is your standard Unix method of creating a new process. And forking will produce a nearly identical copy of your original process. It's going to have the same virtual memory contents. It's going to have the same instruction pointer. It's going to have the same file descriptors, with one exception in that it has a different return value from the actual call to fork, so that we can go through a different code path when we return. So in the shell, that code path is going to take us to this function called run command. So we see somewhere around here we forked, and then we ran run command if we were the child. And what run command is going to do is it's going to run this other function called execvp, which is kind of complicated. It's a C library function that goes through our path, that's what the P means, and tries to find a binary with the name of the first argument that we gave it. And that's a little bit complicated, and we're going to skip over that because it's not as interesting as what actually happens when we execute a binary. So we'll pretend that we've found the binary that we're looking for, and we're going to talk about the exec system call itself. So exec needs to load and parse a binary. ToaruOS uses a binary format called ELF. It's the same binary format Linux uses. It's the same binary format BSD uses. If you have a PlayStation, it uses ELFs. The first thing that we need to do when loading our ELF is we actually have to read it from disk. So now for the first time in this talk, we get to talk about file systems. So ToaruOS's primary file system is X2. It's an older version of the file system that is currently most commonly used in Linux, X4. X2 tracks files as a structure called an inode, and an inode has a bunch of pointers to things called blocks, and blocks are the actual data in a file. And when we want to read a file, we need to look at the inode and find out what blocks we need to read from the disk, and then we have to actually read them from the disk. Our X2 driver actually has a cache of blocks that we've already read, but since we're loading a new binary, we probably haven't read any of these, so we're going to have to actually read them from our hard disk. And once we've read the binary into memory, we now need to actually put it into the right place in memory to run it. Because our binary can't just run anywhere, it needs to run from particular locations, and it's got lots of little pieces that need to be arranged to form a final process image. Once we're done with that, we can finally jump to user space, and now we're running our fetch command. Ooh, finally. It only took, what, 15 minutes? So fetch is kind of interesting. It's a little in-house tool I made that's sort of based on wget, but it's a little bit different. And it uses a special feature of ToaruOS that's called the network file system. So instead of opening a socket using the standard BSD sockets layer you see in Linux, we open this file dev/net/toaruos.org:80. And what that does is we have a module in our kernel that's going to parse this, find out what port we wanted to connect to, get an IP address from the host name that we gave it through DNS, and it's going to then create an internal socket object that we can read and write from. And when we read from this virtual file that we have, we can read packets, and when we write to it, we can produce TCP packets that we're going to send back out to the network. So the first thing that we'll do over here after we've created this is we're going to send our HTTP request headers. And then our network card is going to receive a response from the server eventually. And when it does that, it takes the response that it has, it looks through all of the different sockets it has available, and it appends the data that it received into a queue for that socket. So eventually our web server is going to respond. We're going to parse the response from it, and then we're going to print it out to our terminal. As it turns out, we actually just printed a PDF to our terminal, which was a bad idea. So hopefully that gave a very detailed explanation of how the operating system works. And now we're going to do something a little bit different. I'm going to run a bunch of demos. So there were several different things that people wanted to see working in the OS. And we'll just get started here if I can find out where my... There it is. OK. Move some things around here. Make sure this terminal, that's not the right terminal. I'm really bad at Windows Focus. Set scale 5. All right, so my first demo we have is I have a port of Vim, everyone's favorite editor, right? Right. And I have a port of GCC. So we can build C applications. Pretty cool, right? No? Oh. Well, if that's boring, okay, how about Python? Everybody likes Python. Python port we've had for a little bit. It's not quite complete, but works reasonably well. Now, if that's not enough for you, everyone's favorite terminal application, I think. So if you're familiar with the Nyancat terminal application, I wrote that. And it actually started out as a demo for ToaruOS, so this is its native habitat as opposed to running over telnet servers. And if that wasn't exciting enough for you, I've got something better. Let's play Quake. Unfortunately, I'm not all that good. Terrible on this projector. That's fine. It's so old that I'm bad at the original. Let's try. That looks better. Use our mouse. All right, let's play some Quake. I'm really bad at Quake, so we're gonna play easy. I'm also really bad at this jump. I've done this so many times, and yet I still miss sometimes. All right. Yeah. Kill those bad guys. And the dog. It's like the first thing you kill in this game is a dog. It's so sad. Column. Normally that gives him immediately. Let's go get the nail gun. All right, and then this door opens. Nail gun. Run over here. I actually figured out what these buttons do. Does anyone remember what these buttons do? Well, I don't care. We don't have enough time for that. There we go. So yeah, Quake. Quake is fun. So I thought I'd talk a little bit about what our plans are for the future with the project. So we've been doing this for 5 years now, and I think I'd like to still be doing this for the next 5 years. So our goals have changed a lot since the beginning. We're no longer here to learn POSIX or systems level x86. My C is pretty solid. I'm not really learning much more there these days. Our current goals are mostly porting software, which is why we have stuff like Quake and Python and GCC. Working on the GUI, which is already pretty nice, but there are a lot of little usability problems here and there. And one of the most important goals is to write clean code, because there are a lot of eyes looking at ToaruOS now, and it's really embarrassing when I write bad code and people look at it and they're like, this is terrible, and I'm like, I'm sorry. So what we're looking to do in the next few years is I'm working on a new kernel. Because as I said way back in the beginning, the current ToaruOS kernel is 32-bit only. So the new kernel I'm working on is a 64-bit SMP-capable kernel. It's not quite ready for showtime yet, but I'm working on it. Over the course of the next year, I'd like to port a web browser. There's a web browser called NetSurf that's really good for embedded applications. It's not got a lot of dependencies, so trying for that. I really want to port WebKit, but WebKit is like 10 times bigger than this entire project, so it's a little bit harder. Looking into the far future, we're hoping to port glib and GTK+, so we can start porting some standard Linux desktop applications. So that's all I have. Does anyone have questions?
Can you talk a little more about porting? Like,
Can I talk a little bit more about porting?
What was hard about
What's hard about what?
the Python port?
What's hard about the Python port? Okay. So porting software is a lot of fun, but also very tedious. So you essentially get maybe like 3 different kinds of applications you can port. You have very, very basic C applications. You build them. They don't have any real dependencies. They run. Everything works. You're happy. Anyone use Lua? Lua's like that. You just build Lua and it works. Some things are a little bit more complicated because maybe you're missing features that the application expects. Vim was a fun port because I had to do a lot of new things in my terminal. I had to support a lot of extra little POSIX things that I hadn't supported up until that point. Python was very interesting because the first time I tried to port Python, I was trying to port Python 2.6, and you can't cross-compile Python 2.6, so I was trying to build it on a Linux machine for my operating system, and it didn't work out. And then I started working on Python 2.7, and they fixed a bunch of things, and you can do that now. And the interesting things about Python are that it expects quite a lot if you want a fully working Python installation. It expects you to be able to do dynamic library loading, which is a really hard problem that we haven't quite finished yet. But you don't need that if you want a bare minimum version of Python. You also have to do a lot of little things to get Python to understand how your system works and how it's different from Windows or Linux or OS X at a layer that's a little bit higher than standard POSIX support. One of the most fun ports I did was Quake, which is why we demoed it. So Quake was a fun port because it involved porting a library called SDL, which is used for general graphics and audio output. So that was fun because SDL is something that you really specifically have to port to your platform. It's not something you could ever just go and build unless you already have one of the existing display platforms and audio platforms for it. So building SDL for ToaruOS was an actual experience. And how do my libraries work? How do my system designs support other software? And as it turned out, it worked really well, and I'm really happy with the results from Quake. It runs great. You can hear the audio. So SDL and Quake were a very fun port. How bad was GCC? GCC is actually surprisingly easy to port, because all it needs to do is read and write files. Yeah, I know, right? It's so gigantic, but it's so easy because it doesn't have any system. There are little things that you have to do in order to make GCC target your operating system, but that's something you generally have to do very early on. But actually porting GCC itself has essentially no additional requirements except that you can read and write files. Paul?
What about the debugging with GCC? So does it require more system calls or things like that?
So the question was about debugging in GCC. So hopefully if I understand the question correctly, debugging GCC itself or debugging things produced with GCC? Produced by GCC.
Debugging are produced.
Okay. So GCC defaults to a debug format called dwarf. It's the standard for ELF. It doesn't really require anything additional to support. The trouble is you need an actual debugger. We don't have a debugger ported. So the standard debugger everyone knows about is GDB. And GDB requires a whole lot of tracing system calls that we don't have yet. They're really, really complicated and have to do with all sorts of very interesting POSIX methods for controlling process state and looking at register values and looking at memory. So we don't quite have that yet, but you can run GDB against a virtual machine that's running your code, and that works. A little complicated, though, because there's a lot of noise from everything else that is running in the operating system. And if you stop it at any given point, you're probably going to end up in the compositor's render thread.
So what kind of tools have you set up for measuring what's going on inside a running instance?
So what tools do I use to monitor what's running in a running ToaruOS instance? So I do all of my debugging under QEMU. I usually have it set up with a serial output that goes to my terminal, and most of my applications do a lot of terminal printing. Printf debugging is really, really useful in operating systems.
No, like tools like
Within the OS. So we have PS. We actually have a proc file system that's very similar to Linux in that there's a virtual file system that you can go and read directories in to find out what processes are running. And then you can look at files within those directories to see what the processes are, various different stats on them, whether or not they're running, stuff like that. So it's a very similar thing to what Linux does these days. How well tested is my OS? So I will say there are a lot of current bugs that still need to be fixed, but we get a lot of, something that's pretty rare in the operating system development world is you don't tend to have a lot of people using your OS. ToaruOS has a lot of people who will go and download it and use it and help me debug things. And on top of that, because we have this advanced GUI, we can do a lot of things at once, which works really well for doing tests. There's a problem a lot in kernels in that it's hard to do things like unit tests, because at some point you have to have a whole lot of things set up so that you can actually run those unit tests and record the results somewhere. One of the things that's planned for the new Misaka kernel project is that I'm building an entire testing framework that will support essentially running a bunch of Python scripts against a running QEMU instance and recording exact memory and register results and all sorts of other things. So we're okay right now. We'd like to be better.
Is it just you, or you use the pronoun we?
I use the royal we a lot, but so like 99% of the code base is mine, but I do have a few extra contributors. The audio stack in ToaruOS was written by a guy at Google. I've had a few little things here and there from people over the years. Back when I was still in college, I had some friends at the University of Illinois ACM work on a few of the underlying features, particularly the shared memory subsystem was a big thing that was a group project among 3 different people. But 99% of the code is mine. I feel it's modest to use we, though. So then it's like, it's not always me.
Use grub.
Do I use grub? So there's always this question from people who start out when building an operating system is, well, surely the first part of building an operating system is writing a bootloader. Bootloaders are terrible, and if you ever decide that you want to write an operating system, do not start by writing a bootloader, ever. x86 is very weird, has lots of little things, legacy features that actually turn out to be misfeatures, and bootloaders are all just about getting rid of that. So what a lot of people will do when they realize that bootloaders are dumb and no one should be writing their own bootloader is they use a bootloader called grub. And I do use grub on my CD images, but I boot things directly with the multi-boot protocol in QEMU when I'm doing debugging, which means that QEMU actually knows just where to put my kernel to start it up, which is really useful. It's a lot faster than trying to build a grub image and having grub run and waiting for grub to actually start up. Those milliseconds count.
So you ported libc and you didn't have to push it. Did you put libc? And the second one is like, does the operating system model show exactly, like?
I'll answer. OK. So the question was, what C library am I using, and are all of our device drivers in-house, essentially, right? Yeah. OK. So I'm not using glibc. I'm using a C library called newlib. It's much smaller. It's a lot easier to port. Doesn't quite have as many features, which bites us a lot when we're going to port more advanced things, but it's enough to run stuff like Quake and GCC, so I'm happy with it. As for device drivers, all of our device drivers are in-house. Every single part of the kernel itself is entirely written by me or my team. When we get into user space, there are a lot of like little libraries and things that we use from third parties, Cairo FreeType, libping, stuff like that. But the kernel is all entirely in-house, including device drivers. What's the real world future I see for this? So that's a question a lot of people ask. You're building an operating system. Do you think people are going to use it? Do you ever see it like, is it ever going to take over Windows? I'm doing this for fun. I don't really see any real world future for it, but it is a lot of fun, and you learn so many different things, especially when you get into an operating system like ToaruOS, where we have everything from the bottom to the top. We've got advanced GUIs and we've got kernel drivers. So I don't really see a real-world future for the project, but it's still been a lot of fun. Paul again.
Yeah, I have, recently I was reading up on, and I was wondering, have you ever considered writing your own hardware emulation?
Virtualization layer.
For KVM to make some stuff here to develop or whatever?
All right, so the question was, do I have my plans of my own to write a virtualization or hypervisor layer for ToaruOS, such as Linux has KVM, OS X has something these days. I'd love to. It'd be a really fun project. It's not really on my roadmap at the moment because it's not really related to a lot of the things that I'm doing right now. It's more of an advanced topic, but there's definitely resources out there for people who want to get started with stuff like that. And maybe not now, maybe a year or two from now, I might look into it.
Did porting the SDL library require you to get into OpenGL or any of that?
1 second. I gotta drag that. Make sure I'm showing that. Let me run that while I'm answering the question. So the actual answer to the question is no, because SDL 1 doesn't have any real dependencies on OpenGL. It's an optional thing that you can sort of link in. That said, I have ported Mesa, which is the standard implementation of OpenGL in software for Linux and BSD. It's also the interface to get to hardware when you have hardware drivers available for OpenGL. Video card drivers are like insanely difficult. So I don't have any real hardware acceleration support for OpenGL, but I support OpenGL. So that's running at about 1,000 frames per second. It's hard to see because you only get like 60 hertz on the display, but anyone else? It was a great number of questions, so I'm happy with that.
It completely skips X11 stack, right?
There's no X11 in this. I hate X11. It's terrible. I should note my compositor, it's all in-house. It's probably my favorite project as part of the OS that I built. It's the second version of my compositor. I wrote an earlier one in 2012. It was pretty terrible, and in building that, I discovered a lot of little flaws with the kernel. So I decided, hey, I'm going to build a new one, and while I'm doing that, I'm going to find all the little things that were problematic about building the first one. I'm going to fix them first, so that when I build the new one, it'll be awesome. And I think it's awesome. I might be biased, though. So my new compositor is, do you know what Wayland is? So my compositor is based on Wayland. The name is actually a reference to Wayland, so this is called Yutani. And if you have watched Alien, the name of the company in Alien is Wayland Yutani. I thought it was creative. People on IRC laugh at that joke. At least they say they do. All right.
Thanks, Kevin.
Thanks, everyone.
Right, fuck X11.
Yes, fuck X11. And I have a very special, unique view of that because I was a developer for Compiz
Wait, really?
back in 2010.